Hello everyone, this is Hacking Hardware with a $10 SD card reader, an Exploitee.rs production. Alright, so a little about us. My name is Amir Etemadieh. I go by @Xenofx on Twitter. I'm a senior research scientist at Cylance. I'm founder of Exploitee.rs and also founder of PayScript. We have CJ here, so please stand up or wave or whatever.
Howdy, howdy.
He goes by @CJ_000. He's a security researcher at Draper, and he does hardware and software exploitation of things. And then we have Khoa, please stand up. He is @Maximus64_, and he is a graduate of the University of Central Florida, who is a master of the soldering iron and hot air gun. And so, just as a heads up, this presentation and thoughts are ours and ours alone and have no relationship to our employers. Okay, so there's roughly 10 of us in Exploitee.rs, so we only have 3 on stage. We got to give a shout to the rest of the members. We have MBM, he's the co-founder of OpenWRT. He goes by @MBMWasHere. We have Gynophage, who's the DEF CON CTF organizer, and he goes by @Gyno_LBS. We have Hans Nielsen, who goes by @NonStick, and he is a boring corpsec dude. We have Jay Freeman, who is the creator of Cydia, goes by @Sarek. We have Tom Dwanger, who's the master software developer in our group. And then we have 0x00string, who's actually in the audience. Stand up, Sam.
Come on, up.
And he goes by @0x00string or nullstring. And he's the hacker and troublemaker extraordinaire. I'd like to call him our wild card. Okay, so a little bit about Exploitee.rs. We are a research group who originally started hacking Google TV devices. After Google killed off the Google TV brand, we pivoted and started hacking everything. And so since then, we were previously known as GTV Hacker. When they killed off the brand, we had to change our names, and that's when we became the Exploitee.rs. Since then, we've released root methods for multiple generations of Google TV devices and other embedded systems. And we have a blog, a wiki, forums, all which kind of database are the vulnerabilities we found, as well as community found vulnerabilities. So check out our wiki, and if you have anything to add, let us know. So what are you going to find out today? You're going to find out what an eMMC flash is and how does it differ from NAND, which a lot of you hardware people are probably more familiar with, although you're probably familiar with eMMC as well. We're going to talk about how to recognize eMMC flash, how to identify an eMMC flash pinout, attaching to an eMMC flash within an embedded device in circuit, and then selecting the correct USB SD card reader, which sounds simple, but there's some tricks, and we're going to show you how to limit the pinout that's needed to read and write, so that's an important one. And then finally, interfacing with eMMC flash. Okay, so prior work, just as a note, there's probably a ton of prior work, but we're specifically talking about the prior work that influenced us. Micah Elizabeth Scott @Scanlime, she is kind of the one that introduced us to the subject and kind of got us thinking about it. She has a blog where she built a sniffer for the Nintendo DSi console, and she used it to kind of database the CPU flash read writes. We reference a talk that we did at DEF CON 21 where we had an eMMC root that we released, but we didn't actually go into how you find your own eMMC pinouts and how to communicate with them. And since then, we've kind of developed an approach that's not only low cost, but kind of alleviates a lot of the problems that we found along the way. As I stated earlier, there's probably a ton of you maybe watching this presentation that have had some experience with eMMC. I'm sorry we didn't cite you. There was way too much to cite, so we specifically listed the stuff that influenced us. So, an introduction to eMMC flash. You can think of it as an MMC version of an SD card for embedded devices. The abbreviation eMMC stands for Embedded Multimedia Card. It's inside just a ton of devices, from phones, set-top boxes, tablets, automobiles, you know, anything could use an eMMC that wants a easy-to-use flash device. And it was developed by the Joint Electron Device Engineering Council, JEDEC, and I believe it's currently at revision 5.1 when we made the slides. So, eMMC versus NAND. The big thing about eMMC is that it comes with an integrated flash controller. Normally when you have NAND, a NAND chip, you have an external controller, and the lines that you pull out from flash to that controller and to the CPU, it goes from 8 data lines, 5 control lines for NAND to an eMMC, which we can lower the amount of data lines needed to 1 and then 2 control lines, making it a lot simpler for someone who's working from a reverse engineering standpoint to find the pinout and then communicate, read, write, dump, whatever, with that particular flash. The internal controller handles wear leveling, bad block management, and error correcting code, as well as a few other things. It's constantly being developed as each revision comes. It also provides an easier to incorporate design because it allows an engineer to have their design have the controller and the flash within a single die package. So it's gaining prevalence and actually possibly starting to be phased out by a different type of storage called UFS. So prevalence, it's kind of a boring slide, but 2014 NXP presentation estimated 4.375 billion 16 gigabyte eMMC chips in the world. The number sounds crazy, so we cited the source in our white paper, which feel free to check out if you feel like you'd like more info on this. And the Samsung Galaxy S to S5 mobile phones all use eMMC flash storage. Amazon Echo, Amazon Dot, a lot of Amazon devices actually in general use eMMC flash. So it's in more devices than you would ever expect. It's sold over 110 million devices alone for one device line, which is the Samsung Galaxy S to S5. It's low cost, there's many storage sizes, small single package footprint, which I mentioned earlier with the integrated controller. So how do you identify eMMC flash? There's multiple things that you can kind of do, and this is a kind of generic list because it's a kind of case-by-case basis. When you're looking at a board and you have all these components, it's important to kind of just know where to look, and especially the bigger board, the more components you have, the more likely you'll want to use some characteristics to identify what components you should be looking at data sheets for and kind of identifying which is which. Some of those are the location on the board relative to the SoC. So essentially when you have a memory or flash chip, you don't want to run data lines all throughout the board and impact data speeds. You want to have it as close to the SoC as possible. So that could be on the other side of the board, pulled through the different layers, or it could just be directly next to the SoC. There's a standardized package type for eMMC. It's generally BGA. I'm sure someone could make some other version, but just the standard is BGA, which stands for ball grid array. As I mentioned earlier, you can look at the data sheet. You do that by looking at the chip markings or the silk screening. For chip markings, we're talking specifically about the manufacturer name, model number. A lot of times model number will also include the size values. And then silk screening, in some cases you'll get lucky and it will be labeled flash or eMMC flash and have all the pins labeled as well. You can also look at PCB traces and resistors, and what we're talking about here is specifically if you have an eMMC flash chip or a flash chip and you have a number of resistors pulled off to the side kind of in a line, which we'll show you an example of later on. You might be able to infer that those might be the data lines or based on the number and the location, be able to kind of put it all together that it is eMMC without having a data sheet or the model, a data sheet available or being able to 100% identify the chip based on the model number. So location on board, I talked about this briefly just in the last slide. Most devices you're going to see have some form of MCU or SoC, which is the main CPU plus I/O interfaces and the memory controller. And then you have like a RAM chip, and then you have your flash memory. A lot of SoCs, they have a limited amount of storage space on them. So they have an external storage where they store the code to run whatever the device is and interface with the peripherals. Those memory types would be eMMC flash, NAND flash, NOR, SPI. There's a bunch of different types of flash. with eMMC being kind of the middle ground in terms of communications, SPI probably being the easiest to communicate with, and NAND and NOR being whole other things. So you're going to be looking for BGA packages near the SoC, because as I mentioned, the data lines probably aren't going to want to run too far around the board. Common flash packages. So on the left side you have the ball grid array, which is the BGA package, and it's standard for eMMC. And then on the right side you have the thin small outline package, also known as TSOP. That's typically used for parallel, NAND, or NOR flash. We didn't have the SPI flash on here, but you'll normally see that with 8 legs and kind of a small package, and it'll generally have a lot less storage than these counterparts. So eMMC chip identification. In this particular one, you can see that the manufacturer's name is the top line, big bold print. In this case, it's Toshiba. You can see the part number THGB M5G6A2JBAIR. And then having those two, you can do an internet search for the part number, find the full data sheet. That'll list things like the logic level, pinouts, stuff that'd be good to find. But in some cases, you know, you're reversing a console, you're reversing something that's has proprietary hardware, you might not find a data sheet for the eMMC. You can generally, in some cases, use the same pinout, but you're going to want to check and make sure that they didn't change something, or at least know that you're risking bricking your device if you guess incorrectly. Visually identifying pins or pads. The thing here is that we like to think the last thing you want to do is detach a BGA chip. My failure rate, I have a 1 in 4 success rate. Khoa here, he's close to 100% when he's detaching, reballing, and reattaching BGAs. So, you know, amazing. And CJ is probably just slightly better than me, maybe half.
Barely.
Barely, okay. But so when you're identifying them, kind of the characteristics that you'll see is on the left side of the chip, you'll see all the data pins. The blue pads or the blue circles that say DAT and then the number are the data pads. You'll find probably 8 of them. And you'll notice on the right side of the chip, you'll see the command and clock pads. It's important to notice that they're kind of on the other opposite sides of each other, and that helps you identify if you're looking at a BGA chip and you see traces running to the left to maybe a resistor bank, or even just in some uniform way over to the SoC, you might be able to guess that they are the data pins. And on the right side, if you have 2 coming out and kind of routing around the chip, maybe around all the no connects, you might be able to guess that they're the clock or the command if they're not VCCQ or VCC, which are the power lines. The white pads on this particular,
you totally blew over, it's okay.
Yeah, I went over his slide. Sorry, buddy. I'll give it to you next. The white pads are the no connects, and they are there because flash has a large footprint, and it kind of holds the chip in place. Some might be reserved for future use to kind of keep the BGA standard. Now, I will introduce CJ to take over. I'm sorry, buddy.
Don't worry about it. Less talking I got to do. All right, so this slide that Amir just talked about was everything I was going to say. So we're good. I don't have to say it. It's fabulous. So what's super awesome, when you pull the data sheet itself, what you can actually do is take the data sheet, import it into a photo editor, say GIMP, Photoshop, whatever you like. You could use Microsoft Paint, although I think Paint 3D came out, so Paint's not really around anymore. Question mark. Kind of painful. But you can actually remove the background from the image and then overlay it over the previous image, leading to something like this. So you have a visual representation of where each pad is on the chip. So you see on the blue ones on the left-hand side, the blue ones on the right-hand side, and kind of roughly where they map to on the circuit board. So looking at the ones on the left-hand side, the data ones, which are a little hard to see, but you have the slides at the URL below. Those are the data lines, which are the data pads, and they kind of trace out, looks like there are traces on the circuit board from those pads going directly to a bank of resistors on the side that are labeled from R21 to R28. Keep in mind this photo is slightly backwards and upside down. It's for consistency so you can read the part number. So moving forward from that, they're talking about the silk screening. You see R21 that's near the bottom. You have R28, R21, R23, R20, blah, blah, blah. We'll get into it in more detail in a little bit, but eMMC utilizes up to 8 data lines, Data 0, 1, 2, 3, 4, 5, 6, 7. And just kind of as a bit of a guess, if you're laying out a PCB and you're going to silkscreen markings for what resistor does what, the one you start with lowest is probably data 0. It's just a hunch, but we're assuming so, and we know these lines need to connect to the system on chip. So if we go back for a moment, just to look at the picture, I know, everybody hates me. The system on chip on the left, you see the resistor bank, everything's kind of going that way. And I know, I totally hate when people do that, but it was super useful. They trace that way. Those are probably our data lines. We also need to find our command and clock lines that are normally on the right-hand side of the chip. Of course, we can't really see what's on the right-hand side of the chip. We see nothing comes out. We don't have an X-ray machine in our homes. That would be so cool if we did. To actually see what's through this chip, and we don't necessarily want to remove the chip yet. So we can take an educated guess. If you look at the top left-hand corner of this image, and you see R8 and R9, that those are probably the command and clock lines, based off the fact that one, we can't see where they go, and two, they lead to the system on chip. Now, if you're kind of insane and highly skilled like Khoa is, you will just skip straight to removing the flash chip. It's kind of a difficult thing. It's usually a lot easier to remove than replace, but one step at a time. You can either use it with a soldering rework station or even a heat gun or a paint gun you can get at Home Depot or Lowe's. Take it to it, start heating the board up, pull the chip. I've only had luck with getting the chips off, not putting them on. Khoa's had considerable luck doing both. He's amazing. You also do need tweezers, some soldering flux, and patience, because you don't want to heat the board up too much. You need to heat it slowly, low and slow, and you get it there. So really quick primer. We're not going to get into terrible details about this, but to pull the flash, warm the board gently. You then apply flux, bump the flash chip a little gently. If it starts to move, you can then cleanly lift it straight off. And if you do it right, you don't need all the balls, as in this picture, are still completely intact. From here, you can now trace out each pad and each pin to the resistor bank or wherever it might happen to go. If it disappears, whatever it might be. You can also, from here, leverage that information. Say you pull the flash chip off, and you're like me, I can't solder it back on, and I don't want to mail it to Khoa because it'd take too long. I can buy another one. Could hook it up, as we'll talk in a bit, pull the file system off, pull the firmware off, maybe get crypto keys, get something off that flash chip to leverage it for an exploit or a network exploit, something that we can then use without having to reattach and go from there. So, say you don't, guessing is kind of hard. It could cause damage if you guess and check, apply the wrong voltage, stuff like that. Or, you connect 3.3 volts to a 1.8 volt line, which Khoa will talk about in a bit. Not that he's done that, we have a solution for that. You can test it with an oscilloscope. If you wire up an oscilloscope to what you believe your pins are, you're looking specifically for the data 0 command and clock lines. As Amir talked, you only actually need a handful of pins, which is why this makes it so much better than using NAND flash apart from the controller. So we'll give you a few details. Moving on, general clock signal provides for a constant, steady, repetitive signal. Generally looks like a sine wave in the upper right. It could look like a square wave right below it. Thank you, Wikipedia, for the image. The clock signal is used to synchronize the data in command lines. You want to make sure when the command gets sent, saying, I want block X, and you get block X back, that the timing's correct, so you know what command was sent, what data comes back, and how it correlates. So this is what a clock signal looks like on an oscilloscope. As I mentioned, it's very periodic, very repetitive. It kind of looks like a clock signal. So using this image, and if you're testing things out, you can kind of find a signal that looks like this. It's probably a clock. The command signal, next, you can see represented in this image, the clock signal, very periodic again. The command has little chunks of essentially commands that get sent. You have little bits of commands that go out, and it correlates with the data, not shown in here, but pretty much I'll send a command saying, hey, I want block 0, and it'll be like, okay, here's block 0, and the data comes across, and rinse and repeat to read and write everything. It is worth mentioning the command line is actually bidirectional, so if you send a command saying, hi, I want this, it'll be like, okay, and separately, here's data. And what this looks like on an oscilloscope. Down below is the command line. It's usually easier to identify than the data line, since there's only one. You can see the data line at the top, and there is a rough correlation between data coming across the command line, data coming across the data line, like I said, whole command request, then you get data back. So now let's assume We've got possible paths identified through one of these means, either scoped it, used visual identification, the manufacturer was kind enough to just label everything for me, I found schematics somewhere, something like that. There is a bit of test and reset, guess and check between either a scope or wiring to confirm data 0, command, and clock. Of course, each device is different, and testing will definitely confirm the identity of what pins are what. And then if you have that found for a device like an Amazon Fire TV, that one schematic works for the millions of devices out there and you're good. So it's only a little bit of initial work and you can get pretty good. So fun fact, as Amir was talking about earlier, the SD card protocol is actually a superset of the MMC protocol. So MMC was around first, SD came around, incorporated some of the MMC features, added a bunch more, did a bunch of stuff. Specifically, MMC, in our case, we're only going to be using 1-bit mode, so we only need one data line. Fewer wires, much easier to use. An SD card, normal one that you have in your camera and all that stuff, uses 4 data lines. It is faster throughput than 1-bit. That is also the maximum for an SD card, data 0, 1, 2, and 3. 8-bit mode, only eMMC chips have 8-bit mode, which are data 0 through 7, and has the fastest throughput. So again, reinstating, you only need data, command, clock, also of course power and ground, which we'll get into, to make everything work. So looking at an SD card for a minute, you also need an SD card reader that supports single bit mode. So with single bit mode, the best way to test for it is to just take a normal SD card, take some tape, or your choice of covering, and cover up those lines, data 1, data 2, and data 3 at the top and bottom. Plug it into an SD card reader. If it works like an SD card, you've got a 1-bit reader. The one we prefer is the Transcend RDF5 USB 3.0 reader, and it's actually under $10. I think it was $9.51 last night on Amazon, but don't quote me, but it was still less than $10. So a little bit of savings. I guess wire costs something. So now you want to connect to eMMC Flash. You've got a couple options. You can do it in circuit. So you have a box, you open it up, you solder to it, you've got your pinouts, but you need to apply power. You can either self-power it, have a power cable plugged in, kind of do your thing. That has some challenges. You can separately power the flash externally, so have like a bench power supply or a USB breakout and kind of power it up. You can also debug as shown in this picture, which Khoa has done because he's literally insane but amazing with soldering, and solder to the backside of a BGA Flash chip to extract the data. Each method has its own issues. Debugging obviously can be a challenge. Not impossible, but difficult, takes a bit of skill. Again with the dead bug, it looks like a dead bug. It's on its back, the wires are hanging up, and it is very effective. It is the best way to get data off. You will never fail with this method, assuming the skill is kosher. So if you can do it, you will not fail, you'll get data off. But it's used as a we like to use it as a worst case scenario. Khoa will use it as a first case scenario because he's amazing. To reattach it, since you're soldering to the balls, you've got to reball the chip. There are ways to do this. There are kits. There are things online. Not preferred, totally possible. Now for in-circuit programming, I'm going to hand it over to Khoa.
So when you try to access the eMMC in circuit, the CPU may try to attempt to communicate with the eMMC chip. This will lead to data corruption, and in some case you can't even detect the chip. To prevent this, you need to hold the CPU in reset, find the reset pin and then put low or high depending on the chip. Or you can, some device have a reset button on the back, you can just hold that button. Or you can disconnect the eMMC line from the CPU, or you can disable the CPU oscillator. Logic level is also another issue when you're trying to access the eMMC. Most embedded device use 1.8 volt logic level for the eMMC, and the SD card reader, the USB SD card reader, only operate at 3.3 volt logic. So you cannot change the eMMC logic level to 3.3 in circuit because this is physically connect the VCQ, which has the logic level to 1.8 line. So when you feed 3.3 to a 1.8 line, all the device on the same power rail may get over voltage and could damage the device. To fix this problem, we make a low voltage level adapter, which translate 1.8 volt logic into 3.3 volt. So some troubleshooting some important consideration for troubleshooting. A good ground connection is very important, and the length of wire can be impact the connection too. The logic level must be known to properly communicate with the chip. You ensure a good connection to all the port, and you have a clean power source. So here is our low voltage eMMC adapter. It's convert the 1.8 volt from the eMMC to 2.3 volt that the USB reader can use. It's utilize a TI SDIO bus voltage translator. It's open source, and all the schematic and the design is available on our website. Here's our breakout board we also make. You can use this with a SD card reader to read 3.3 volt logic level for the eMMC. So this board is different from the last one. This one doesn't have the voltage translator on it, so you can only use for 313 or that button chip. This doesn't have any component on it. It's just a passive board. Yeah. And another special thing about the eMMC boot partition is to have the special boot partition. You have to send a special command to enter this mode. With a normal SD card reader, you cannot send that command to enter the mode. So you need a SDIO controller. With the SDIO controller, when you hook up the eMMC, it's automatic detecting as MMC block 0, boot 1, boot 0 in the Linux kernel. So some laptops have a SDIO interface for SD card reading. It supports a special command needed to interface with the boot partition. So PC doesn't have this SDIO controller. You can buy a PCI Express to SDIO bridge. It's called a RITCO R5 U230 board. It costs $150. Or you can use a BeagleBone Black. It have a SDI interface, and you can just wire up to the eMMC that way. It only costs $50. So here on the picture, you can see that I wired the SD card slot into a pin header. So you can just wire that to an eMMC. Then the boot partition will just show up in Linux at def MC block, then boot 0 or boot 1. And here, for the demo, Amir will show you.
Thank you very much, Khoa. I don't know if this will work, but can we get a little round of hand for him? This is his first time public speaking, and he's doing it at Black Hat, so you know, big credit to Khoa. So yeah, let's do this demo real quick. So guess I'll have to exit the show. Okay, so we're going to do it at 4 times speed because this is an 11-minute video. And it's going to look a little crazy because it's at 4 times speed. Actually, this isn't sped up at all. This is just how fast Khoa works. So first part's a little boring. He's just showing the device booting up. Essentially, here in a second, he's about to take it apart. And this is the pinout for the Fire TV. It's quick, but you can see it on our wiki. We got that pinout by the process that we talked about in this presentation. He's doing an in-circuit programming of this particular chip, but in that picture you could tell that he had detached it, ended up having to reball and put it back on. So, I kind of wish you guys heard the audio on this because we terribly put some really bad techno on it. We last minute decided to have no audio. So yeah, this process here, he's removing the clock resistor so that he can have in-circuit power to the chip, essentially stopping the MC or SoC from communicating with flash and allowing him to only have to connect DAT0, clock, and command, and ground. So I know the talk 5 pins, but technically this method is 4 pins. And once he gets connected, what you're going to see is he modifies the file system, adds SuperSU, this is an Android-based device, and then brings it back up and you have root. The beautiful thing about communicating directly with eMMC is there's no exploits required. You're just using your hardware abilities to communicate directly and modify the chip, and then just boot it and everything's great. As long as there's not signatures or some form of secure boot on that particular partition or image, then this is a great solution for projects as long as you spend the time figuring out the pinout or pulling the chip off. So this part's not as important, but it's just showing him adding the needed files to the file system. You can see that it recognized that it was connected to his SD card reader. All done. Now he's just removing the wires. All right. Cleaning everything up so he doesn't create a short. And yeah, this would have been way more boring at 1x. So there we go, back together and showing it's up to date and rooted. So it's a great thing to be able to know, and that's where we felt the value was of coming and bringing it to you all at Black Hat, because we've had a lot of people jump into our IRC channel and tell us how they haven't been able to figure out a pinout or are having issues connecting. And so we're hoping that clears it up. So now we're going to open it up to questions. Keep in mind we do have some freebies to give away, so if you're leaving already, then so be it. We got 2,000 of these things. So anyone have any questions? What was that? Who does my hair? Bird's Barbershop in Austin, Texas. Okay, so no questions. That's easy. Oh, there's one. Okay, what's your question?
I can't believe how many MC no connect balls are on those BGA chips. Aren't there any variants which don't use that many non-connected balls?
Okay, so the question is, do y'all mind if I take this question?
Go for it.
The question is, why are there so many no connect pads on the eMMC BGA chips? We're not the ones that built it, but I can tell you what we believe the correct answer is, and that is that those pads are holding that big package onto the board. Beyond that, they're enforcing the standard of BGA and the amount of pads that would be used in any BGA format, because this is not specific to eMMC. So it's more of standard with also the benefit of holding it to the board. Next question? Or did I answer that question? You're good? Okay. Next question? Anyone? Right, super guy in the back.
Can you hear me?
Yes, I can.
All right. So you showed an implementation using a specific Toshiba and also a specific device, but I'm wondering, was there any other or any specific eMMC chips that you had tried that you weren't able to, or different like 1-bit, 4-bit, 8-bit modes that were more difficult to try and hack this way?
So his question is, we specifically mentioned the Toshiba chip, and I believe one other example on finding the pinout and being able to communicate with it. Are there any that pose more problems? Honestly, most of the problems were because of, like we said in the troubleshooting section, long wires. I destroyed one of my readers at one point. eMMC, it's a component for a board that engineers have to rely on a specific set of programming and standards. The biggest problem you'll have is maybe if you're doing in-circuit programming, you don't understand the entire device's schematic or design, and you are having issues with other components on those power rails, or that happen to be utilizing that chip somehow or another. So, best case, or not best case, the best solution in that case would be to detach the chip, dead bug it, because then you have a direct connection to flash without any other interferences. Do you have anything to add?
Just to elaborate, we've looked at other types of flash chips, be it Kingston, SanDisk, this was Toshiba, and there are a few more manufacturers. We have not yet had a problem. Not saying there's not a random flash chip that we haven't come across yet that could be problematic, not work with this method. Just with the multitude of devices we've looked at, this has yet to be a problem.
Okay. Does that answer the question?
Yeah, thanks.
Yeah, no problem. Thank you. Anyone else? Okay, right there, blue shirt. Are you signing specifically? Okay. So his question was, we mentioned secure boot and signing being an issue. Have we seen it? What was the end of that? I'm sorry. Honestly, I'm seeing it more and more. The question was, how often do you see a secure boot or a signature check implementation within eMMC? I'm not specific to the hardware, but software side or stage 1 bootloader. It's becoming more and more prevalent as SoCs have some type of secure boot support, some form of chain of trust. Generally at that point, what we like to do is to look at problems with how that is implemented as opposed to, trying to figure out a way to crack the encryption. Like it's more so, I believe at DEF CON 23 or maybe DEF CON 22, we had one issue where they were loading stuff or information from Flash, and we were able to set the memory address, and they had a signature check on the first loaded image and then no signature check on the second with an arbitrary memory location. And so we were able to change that second memory location and had it override the first loaded image that was loaded into memory and provide the second. And so in those cases, you're looking for a flaw in secure boot, and it's one of those things like, we're talking about interfacing directly with the hardware. It really depends on software if secure boot becomes a problem or not.
But it is worth mentioning that device in question actually used an eMMC flash. So we were able to pretty much write, dump, test, rinse, and repeat consistently. And if there were some devices will have you boot multiple times and fail, it will wipe the bootloader. This one actually did. It was the 10 times and you're out. We were able to just write it back and keep trying. So with this method, we were able to constantly test and repeat without needing to buy new hardware all the time, and still eventually crack the signature, or at least bypass the secure boot.
Okay. Did that answer your question? Great. Any other questions? Okay, gentleman with the tie. Speak a little louder, please.
Use the microphones in the back.
He asked if there was an underlying file system. Did you say requirement at the end of that? Or? It's you think about a USB storage device, you think about an SD card. You're generally you have storage space and you choose your file system. And so there's no specific, we sell these eMMC adapters, and I personally test each one of them before it goes out. And I have this, actually have it with me. I took a Fire TV stick and I soldered it to a breakout board. Probably can't see it, but I use this to test every single eMMC board that we ship out. And when I plug it in, Ubuntu auto mounts the images and it just shows up beautifully, no extra work needed. So it's mounting multiple partitions, so it's reading the partition table, and I think this particular one's like ext3 or ext4. Does that answer the question? Okay, anyone else?
Amir.
Okay, yes.
Amir.
Where the heck?
Amir, in the back.
Okay, yes.
You start with the microphone.
Yeah, so my question is about as newer devices go from eMMC over to UFS, how long will it be before we have pinouts for UFS chips and a cheap card reader?
It's funny, we actually talked about this before we came up, that we knew that a UFS question was going to come out. I haven't looked too much at UFS, so I can't directly speak at that question. Do either of you guys have?
Not so much, but based off the prevalence of the millions, hundreds of millions of devices at a bare minimum out there, and with, when devices are designed, they're still designed for 2 years in the future, we're going to see eMMC still for quite a while. And hopefully in that time frame, in a bit, we'll be back with something for UFS. And we'll go from there.
So yeah, maybe future project. Just keep an eye on our wiki and Twitter. We definitely have talked about that, but we haven't done the research yet to be able to truly answer that question. Did that answer the question? Okay, good enough. He's gone. Anyone else? I think that's it. Someone, like, wave your hand if you have a, because I can't see. Oh, back there, black blob. I don't.
How often, like, does the pinout change much between the different chips that you've seen before? Like, are they actually like the same amount for each one, and you just lay a board on top and just fiddle around for each pins?
So we have 2 BGA variants.
So I personally have only seen one variant, but Khoa says that he's seen 2. Oh, actually, let me repeat that question. Are there multiple variants that we've seen in the past of eMMC BGA pinouts? Was that correct?
Yeah.
Okay. So Khoa said he's seen 2 variants.
Oh, the new one, they say they have the SD card,
Yeah, talk
the
about it.
SRAM on it too.
Yeah, he said he's seen one with, you said SRAM?
Yeah, with a Fire TV when we just recently looked at.
So we've seen one, it was actually this last week preparing for this, that had a different pinout. But for the most part, the majority of the eMMC chips that we have seen have had the identical pinout as that Toshiba. And so that's why I had said that you could kind of guess, you could use an eMMC pinout and probably confirm some no connects or confirm some data lines, preferably within like an oscilloscope, so you can actually see the patterns and the waveform. But for the most part, there's just that one variant, or those 2 variants, and then that one being the more prevalent. Anything?
No, that's kosher.
Okay. Did that answer your question?
Yeah, thank you.
Yeah, no problem. Thank you. Anyone else? Okay. It seems like, unless I'm missing someone, it seems like we're done. Let's see. We want to give a thank you to Black Hat for